We are looking at a 45-year publication record of a single agricultural scientist, spanning from 1972 to 2017. The chronological endpoints of this document represent two different worlds. In 1972, the work is concerned with the chemical soaking of sugarcane sets. By 2017, it is a blueprint for the sustainable agricultural infrastructure of the United Arab Emirates. This raises a mechanical question. How does the day-to-day work of an agronomist move from the microscopic chemistry of a single seed to the macro design of a city-scale food system? We can find the answer by treating this list of titles not as a resume, but as a primary dataset for a bibliometric meta-analysis. This specific CV acts as a micro dataset that mirrors the macro evolution of global agricultural science, tracing the move from isolated chemical interventions to holistic systems engineering. Mapping this specific publication record allows us to see exactly how and when this scope of the industry began to shift. To analyze this, we plot the publications on a coordinate plane, with time on the x-axis from 1970 to 2020. The y-axis measures impact scale, from microscopic treatments to macroeconomic policies. The raw data nodes naturally cluster into three distinct chronological and vertical groupings. These three clusters represent the three major paradigm shifts in modern agronomy. The first and largest cluster spans from 1972 to 2020, anchored at the bottom of our scale. The defining characteristic is syntactic repetition. Dozens of papers begin with the exact same objective, the determination of the optimum level, or optimization, of a single variable. It is a relentless drive to optimize nitrogen for wheat, for maize, for cotton, potassium for mung beans, phosphorus for sugarcane. This is the research paradigm of the Green Revolution. The objective was yield maximization through the isolated control of macronutrients, specifically nitrogen, phosphorus, and potassium, or NPK. In this era, the work was purely empirical. Scientists had to be physically present in the fields, verifying how localized variables affected a specific crop. Research focused on micro-interventions, soaking raw sugarcane sets in micronutrient solutions, or applying pre-sowing treatments to seeds to trigger early growth. The farm was treated as a closed chemical equation, where adding a precise chemical input produced a predictable biological output. Around 2004, the data takes a sudden vertical leap. The focus shifts abruptly from the chemistry of the root toward the macroeconomic ceiling. The publications move away from biological journals and into the Pakistan Gulf Economist. A new vocabulary enters the dataset: ag biotech, clean development mechanisms, and e-agriculture. This shift reflects a point of saturation. After 30 years of refining the optimum level of nutrients for nearly every major cultivar, the research began to address the limits of that approach. The data shows that yield optimization alone could no longer drive growth when faced with external pressures like environmental degradation and resource depletion. The focus moved to how a crop yield integrates into the larger system of international trade law and global economic policy. This era demonstrated that a high-yield harvest is only useful if there is a resilient economic and digital system capable of sustaining it. The final cluster of data, from 2011 to 2017, shows the move into high-level consultancy, with projects spanning British Columbia, China, and the UAE. These reports cover large-scale system design, planning organic rose production for Canada, and managing sustainable agricultural projects for government ministries in Dubai. But how does one accurately model a national bioenergy feedstock industry or a city-scale environmental farm plan? If we connect the points on our chart, we see a tech tree forming. You cannot design a sustainable organic system at a city scale without foundational empirical knowledge of how soil salinity and nutrients work in the dirt. This high-level consultancy is the terminal application of full-stack agronomy. When we view the entire 45-year plot, we see that the micro, macro, and systems eras are not separate. They are an interconnected network. The chronology ends with a single paper in 2017, Food Security, This Century's Key Global Challenges. This topic is the ultimate macro system, encompassing everything from the root-level chemistry of the 1970s to the trade agreements of the 2000s. The decades spent calculating the exact nitrogen requirements for a single plant were the necessary prerequisites for addressing the security of the global food supply. As our food systems scale into complex international networks, they remain anchored to the physical reality of the field. The move to address global food security is the final layer of a tech tree built on 45 years of optimizing variables in the soil.